Let's look at the forecasting timeline for a two-period moving average. This is in the ballpark of where we left off in the previous video. Take a look at time period t minus 2. Let's pretend that's the first time period that's observed. So we don't start collecting data until two periods prior to today. We observe yt minus 2. I cannot use the two-period moving average to forecast for the next period at t minus 2. I just observed t minus 2. I can make a one-period naive forecast for t minus 1, but I can't use the two-period moving average methodology to make a forecast for t minus 1. So I can forecast t minus 1 no problem. I use the naive model. However, I cannot use the two-period moving average model to forecast t minus 1 because I only observed one period. I can't start using the two-period moving average until making a forecast for time t. So I collect the data from yt minus 2. I also collect the data from yt minus 1. That green information I can then split 50-50 to make my forecast for period t. And then I continue to have observed t minus 2. I didn't forget the data point, but I'm going to use t minus 1 and t exclusively to forecast t plus 1. With the three-period moving average, t minus 2 and t minus 1 are insufficient because those are just two periods. I actually need t as well. So that is where we left off. And just a comment about moving average models is that every period is weighted equally. So I weigh t minus 3 the same as t minus 1 if I'm making a three-period moving average. And that may be useful if there are not huge deviations from period to period, but it may be less useful if the more recent past is indicative of what the future will look like. So, think of taking it to an extreme. Suppose we used a 20-quarter forecast for Amazon. I don't know, we're now in quarter two of 2020. I don't know how relevant quarter two of 2015 is relevant to quarter one of 2020. Now, I do understand that there's some seasonality there. However, I have to think that Amazon Prime has really changed the amount of business that Amazon has received in the last 5 years. And I don't know how relevant 2015 is in the forecast any longer, but if we were to do, say, a 20-period moving average, it would count exactly the same as last period. That might seem crazy. So we might look at that and be like, whoa, 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 whoa. I don't know that that should be the case. I think the more recent past should count more heavily. Well, you would be right. And we talk with forecasting about us having the capability and the flexibility to use the previous data in any way that we want. So I'm not restricted to say, hey, look, 2015 has to count the same as 2020 because I'm required to use a moving average. No, that is not a requirement. I'm not required to use 2015 at all. I can downweigh it very heavily. And one of the most common ways of doing that is what's called exponential smoothing. So this is something that I can do if I don't have obvious seasonality or trend in my data set. And we'll talk about how to modify the exponential smoothing model in two ways to account for both seasonality and trend here in a little while. But exponential smoothing solves this problem that we might have of each data point in the past counting exactly the same. So I may not want to throw away the information from 2018 from Amazon's forecast. If I made a four-period moving average forecast, I throw away 2018 because I only go back four quarters, and that's sometime in 2019. I might not want to do that, but I might want to weigh those periods in 2018, 2017, etc. pretty lightly. And so I might want to be strategic in how I weigh previous periods. And in particular, I might want to weigh current periods more heavily. And so how do I do that? I do that with what's called a simple exponential smoothing forecast. YT hat, this first bullet point, YT hat continues to be the forecast for today. So YT hat has the same meaning that it had, if we go back through these slides, for the moving average. Okay, if you take a look at this slide, YT hat is the forecast for today. It has the same meaning as with the naive model here. YT hat is the forecast for today. So there's no difference in the meaning for exponential smoothing forecast. YT hat is the forecast for today. What I do is I weigh my forecast strategically. So alpha is a decimal. It's a weight between 0 and 1. Okay, so alpha is the amount of the forecast that is dedicated to the previous period. So take a look at this formula, the second bullet point. Let's just say alpha is equal to 1 exactly. Then we have the naive model. Alpha is equal to 1, then YT hat is equal to YT minus 1, and 1 minus 1, that's 0. I have no component of the forecast that relies on the previous forecast. So YT hat is equal to alpha. Alpha is a percentage between 0 and 1. It's a decimal between 0 and 1 times YT minus 1 and 1 minus alpha times YT minus 1 hat. So the exponential smoothing forecast incorporates the data and the previous forecast. So let's just repeat that. YT hat is the forecast for today. I use the data from yesterday and the forecast from yesterday. And this is what we call recursive. It holds for any period t. So it doesn't matter if I define t to be tomorrow or the next day or yesterday. Whenever you did it, you're using the data from the previous period and the forecast from the previous period. Now, this fourth bullet point is the kicker. By including the forecast from the previous period, I include all of the previous values of y by default. So the recursive nature of the exponential smoothing forecast actually includes all of the previous periods, all the way back to the start. So, how did I make the forecast yesterday? The same mechanism. I used the data from 2 periods ago and the forecast from 2 periods ago. So YT minus 1 hat is the same as YT. It's the same formula. We just used the same approach. It was just for a different period. Okay, now let's substitute in through this last term. I'm going to plug it right into the formula. I take out YT minus 1 hat. Instead, I have, because YT minus 1 hat is equal to this right-hand side, so I'm just going to plug the right-hand side in here. Okay, so I take this part in the fifth bullet point. I take the right-hand side, YT minus 1 hat is equal to alpha YT minus 2 plus 1 minus alpha YT minus 2 hat, and I plug that portion in for YT minus 1 hat. Okay, and you can see that it's included here in these curly brackets. It's included there. Now, this is the fun part. Everyone should be enjoying this part right here. YT hat. I keep the YT minus 1 hat. This and this are the same. But the 1 minus alpha now has YT minus 2 hat in there. So where does the data for YT minus 2 come from? It comes through the last part of the forecast. And you see this YT minus 2 hat, that's where YT minus 3 is going to feed in there. Now, why is it called exponential smoothing? Let's just take another look. The forecast for YT has the data from YT minus 1. So I have the data from yesterday, and that's multiplied by alpha. I have the data from 2 periods ago, and I have the forecast from 2 periods ago as well. Now I'm going to distribute the 1 minus alpha through. So I multiply 1 minus alpha times this first term. You can see it right here. I have 1 minus alpha times alpha. That's this first part here. And I multiply times the second term. So I just distribute it through the curly brackets. I get rid of the curly brackets, but I distribute the 1 minus alpha through. Now I've got the exponents here. 1 minus alpha times alpha. 1 times alpha is alpha. Minus alpha times alpha, that's minus alpha squared. That's exponential. Okay, 1 minus alpha times 1 minus alpha is 1 minus alpha squared. That's exponential. This is where the exponential smoothing comes in. This is why it's called exponential smoothing. Note, if I were to plug in for YT minus 2 hat, I would have YT minus 3, and I would just keep feeding exponents into this model. Now, what are the practical implications for the forecast? Let's look again at why it's called exponential smoothing. But now I'm going to set alpha equal to some number so we can visualize it. My forecast for today, 80% of the forecast is coming from data from yesterday. Then I have 0.8, 0.8, and 0.8 here. I distribute it again. Okay, so this is the same as the previous slide. However, I just changed alpha to 0.8. Now, I have 0.8 times 1 minus 0.8 here, which is 1 times 0.8. That's 0.8 minus 0.8. Sorry. Minus 0.8 times 0.8 is minus 0.8 squared. Okay, so I have 0.8 minus 0.64. That's 0.16. And then I have 1 minus 0.8 squared. That's 0.2 squared. That's 0.04. 100% of the forecast is accounted for. 80% of the forecast is the data from the previous period. 16% of the forecast is the data from 2 periods ago. And 4% is everything else. Everything else, 3, 4, 5, 6, 7 periods ago. All of that data taken together only comprises 4% of my forecast. Exponential smoothing is a little bit misleading because the previous forecast is in the new forecast. So I think the misleading part is that people don't actually think that there's data from the previous periods in there because they don't see that it was in the previous forecast. Now, previous values of the time series are significantly less important if alpha is high. So if alpha is close to 1, we basically have a naive forecast with just a little bit of feedback from the previous periods. Now let's go back and take a look at the formula for exponential smoothing. You see this yt minus 1 hat. That assumes that we had to make a previous forecast. So how do we get started with the exponential smoothing? What do we do to get started? What do we do to get started? We make the first forecast as naive. So the first forecast of the exponential smoothing model, we just use the naive model. Then we have a forecast that we can plug into the exponential smoothing equation. We use the data in that forecast, and now we start using the equation, but the first forecast is naive. That's in bold. That's very important. What alpha do we select? We'll work on this. So I'll start you off with an alpha in this class, but in real life, you may want to try to find the best alpha. Now, I may not have a theoretical basis for picking an alpha, but what I can do instead is either try some different values for alpha and see which one has the lowest root mean squared error, or I can use the solver function in Excel to explicitly minimize the root mean squared error, and I'll show you how to do that here. Okay, so let's take a look at an example of exponential smoothing. Y is the data that's on the far left column, yt hat is the forecast. Okay, so here are my data. They're kind of clustered between 2 and 3. Okay, now the initial data point is 2. In period 1, my data is 2. I cannot make a forecast for period 1 because I did not observe period 0. There's no error, there's no percent error, there's no squared error. Now in period 2, the data is 3. My forecast is 2 because I used the naive model. The error is 1. 3 minus 2 is 1. The percent error, I take 3 minus 2 divided by 3. The error divided by the data. I missed by 33%. Yuck. Squared error, 1 squared is 1. Now, my forecast for period 3, this is the important part. I take 0.9, that's the alpha, times 3, that's 2.7. Okay? Plus 1 minus 0.9. So I'm applying this formula here. 0.9 is the alpha. 0.9 continues to be the alpha, so 1 minus 0.9 is 0.1. So I have 0.9 times 3 plus 1 minus 0.9 times 2, that's 2.9. Now the date, I make this forecast in the second column before I ever see the 2.75. Now the error, data minus forecast, that should be a minus 0.15 here. And you can see I actually have a minus percent error here, so I forgot the negative here. And the squared error is 0.0225. Okay, let's look at the fourth period. 0.9 continues to be the alpha. The previous data is now 2.75. So I use the 2.75 to forecast the 2.6. Then I observe the 2.6. plus 1 minus 0.9 times, not 2 anymore. I replaced the previous forecast with the 2.9. But note that the 2.9 actually embeds the old data. So I have 0.9 times 2.75 plus 0.1 times 2.9. That's 2.765. And we continue to just feed down. We replace the old forecast with the newer forecast here. We replace the old data with the newer data here, and so forth. Now, to find the mean squared error, you just add up all the squared errors that you calculate and divide by 6. To find the root mean squared error, you take the square root. Now, we can do this in Excel. Excel has built-in exponential smoothing that works similarly to the moving average, but I actually want to show you how to make an exponential smoothing forecast in Excel. So we're going to have alpha as 0.4. I have this data included here. Here are the data. They're in column A. And actually, I'm going to insert a column here, and we'll just call this the period. So this is the data for period 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 periods of data. Now, the first forecast for exponential smoothing. How do I get started? I use the naive model. Okay, so in period 2, the data was 1.2. I did not see it. I forecast 1.1. My error, I take the data minus the forecast, and I get 0.1. Now the squared error, I have the squared error as the error squared. Now, the new forecast. This is where I use the alpha. This is where I use the alpha. I'm going to highlight the alpha right here. We use it all the time. Well, I'll pick a better color so we can all see how it's yellow. Yellow's probably better. All right, now, in order to make the exponential smoothing forecast, let me just type it in down here. We have alpha times the data from previous period plus 1 minus alpha times the forecast from previous period. So these two parts are going to make my forecast, highlighted right here in yellow. So I'm just going to try to execute. I'm going to try to execute this as best I can. Alpha times the data from the previous period. So equal in this column C. Alpha is in B12. I'm going to lock it in. Times the data from the previous period. What was that? 1.2. Now I have plus 1 minus $B, $12. Again, I keep the same alpha as before. Now what was the forecast? 1.1. Okay, and I'm just going to copy that all the way down. I copy my errors. Actually, I'm going to copy these columns here all the way down. Now, how do I find the mean squared error? I just take the average of the squared error. That's the mean squared error. How do I find the root mean squared error? I take the square root of the mean squared error. So I've just made all of these forecasts. Now, what you can see here is that I'm missing by around 0.07 every time. Some of the time I miss by less than 0.07, but you can see that clearly here I've missed by more. Okay, and that is just a feature of the data that I have. But what I want to do is